Okay, so Assalamualaikum. This is your Thermodynamics 2 class, and today is lecture number 18. So, can anyone confirm what's appear on my screen right now?
Yes, sir. Lecture number 18.
Okay, thank you so much. Okay, so as I already communicated with you here that today there is one quiz. Okay, but unfortunately, due to the new instruction from the NUST main office, the quiz will be on LMS. Okay, so it can be in the form of multiple choice question or either in the short questions. Okay, so I will try to develop the quiz in the next classes. Okay, so also it is possible that I will take the quiz in the same form, okay, through the MS team. Okay, but I will have to figure it out that either the NUS main office allow for this. Okay, so be prepared for the next class that it might be the quiz in the form of the same pattern. Okay, that will be the question, okay, or the problem. Okay, or either it will be in the MCQs through LMS. Okay, so for today there will be no quiz. Okay, so we will start towards the lecture 18, which is again from gas power cycle and related to Brayton cycle, which we already discussed in the previous class. So we will solve some other questions related to ideal Brayton cycle. Okay, so here is the question. Air enters a compressor of the gas turbine plant operating on a Brayton cycle at the pressure and the temperature is known to you. Okay, so the P1 and T1 is mentioned in the question. The pressure ratio in the cycle, so it is the maximum pressure, which is towards the ratio of maximum to minimum pressure, P2 or P1. Okay, and it is also called RP. It is equal to 6. Calculate the maximum temperature in the cycle. So if you already correlate with the TS diagram, so maximum temperature is at the exit of your combustion chamber, or either it will be the inlet of your turbine section. So it is point number 3 which we are talking about. So assume the turbine work is equal to 2.5 times of compressor work. Okay, so this is another statement that is given in the question, so where WT and WC are the turbine and compressor work respectively. Okay, so you have to find the cycle efficiency. Okay, so you have to note down the data, then we will try to solve the question. Okay, so quickly draw the TS diagram first. So the TS diagram of the Brayton cycle. So your 1 to 2 process, compression process, then heat addition process, expansion process, and it will be the heat rejection process. 1, 2, 3, 4, Q in, Q out. Okay, and P is equal to constant over there, P is equal to constant over there. Okay, so now from the statement, so first thing we have to find is the maximum temperature. Okay, so calculate the maximum temperature in the cycle. So what we have to do, we have to find the T3. Okay, so in order to find T3, so the data which is given in the question is T1 is given, which is 27 degrees Celsius or equal to 300 Kelvin, or P1 is also given in your question. Okay, 101.325 kilopascal, and the value of RP is also known to you, which is pressure ratio, which is equal to 6. Okay, so now we can apply one relation, which is the isentropic relation for process 1 to 2, because we are interested in to find the point number 3. Okay, so we can apply T2 over T1 is equal to P2 over P1, K minus 1 over K. Okay, so this is the relation which is valid. So I already told you that RP is the ratio of maximum pressure to minimum pressure. So P2 or P1 is known to you in the question. Okay, so from here we can easily find the value of T2, which is 300 into RP value is 6, specific heat value for air 1.4, minus 1 over 1.4. So if you can solve it, you will easily get the value of T2, which is equal to 500.4 Kelvin. Okay, so now we will move towards the T3. Okay, so we can apply another relation, isentropic relation for process 3 to 4. So T3 over T4 is equal to Rp. Again, it is a pressure ratio because P2 is equal to P3, or it is also, you can say, P3 over P4. Okay, so Rp K minus 1 over K. Okay, so from here we can generate one relation from this equation, which we can say T4 is equal to T3, or if we can just put the value of Rp and the K value, so it turns out to be 1.668. Okay, so this is another equation for T4. Okay, so now in the question it is mentioned that the turbine work is equal to 2.5 times of compressor work. Okay, so from here we can try to solve for value of T3. Okay, so because we have to find the value of T3 in this part A, 2.5 W compressor. Okay, so for the turbine, we can simply write that it is equal to mCp T3 minus T4, or is equal to 2.5 times mCp T2 minus T1, because compressor is between 2 to 1. Okay, so this relation come from simple because I already told you whenever that if we can write for the compressor, for example, H2 minus H1, okay, which is the delta H. Okay, so it will be equal to mCp delta T. Okay, so from this relation, which come from your chapter number 7, I think. Okay, so which we already discussed in the previous classes as well. So we can easily write in this form. Okay, so now simply you have to put the value of T4, which is equal to T3 by 1.668 over there, and then you have already have the value of T2, okay, from this part, and T1 is mentioned from your question. Okay, so you have to solve it for T3, or M value, okay, it will be cancelled, and CP value is also cancelled because it is the same. Okay, so if you can solve it for T3, it turns out to be 1251 Kelvin. Okay, so this equation I have just solved for T3. Okay, so this is the required thing for your part number A. Find the maximum temperature of your cycle. Okay, so you have to note it down, then move towards the second part, which is just find the cycle efficiency. Okay, so as you already know that the cycle efficiency for the Brayton cycle is equal to 1 minus T4 minus T1 T3 minus T2. Okay, so this is the relation we already see in the previous lecture. Okay, so now we have the value of T1 with us from the problem statement. T3 we have just find in the previous slide, and T2 also we have find in the previous slide. Okay, so now the question is where is we have to find the value of T4. Okay, so as from the part number previous part, so we already developed one relation which is T4 is equal to T3 over 1.668. Okay, so T3 value is known to us from the previous part. So simply you have to put the value 1251 and you just have to divide by 1.668, and it turns out to be the value of T4, which is 750 Kelvin. Okay, so now we have all the values with us. So simply you have to put the value of T4, which is 750, T1, which is 300, T3 value, which is 1251, and T2 value is 500.4. Okay, so if you can solve it, it turns out to be 0.4, or you can say it will be equal to 40% of your thermal efficiency for Brayton cycle. Okay, so simply you also have to use the relation which we already developed. Okay, so it is on you, whatever the relation you have to use, 1 minus 1 over rp k minus 1 over k. Okay, so because rp is known to you, k value for air is already known to you, 1.4, and you simply put the value and you can get the thermal efficiency, and it will be equal to same 40%. So you have to note it down. If you have any question, you can ask me. Then we'll move towards the next question.
तो इसमें क्वेश्चन में स्पेसिफाई तो नहीं किया जाएगा ना कि कौन से मेथड से निकालने, हम अपनी मर्जी से निकाल सकते हैं ना, या फिर
जी बिल्कुल, अगर आपको मेंशन नहीं है कि एयर स्टैंडर्ड एजम्पशन यूज़ करनी है या वेरिएबल स्पेसिफिक करनी है, ठीक है, तो आप किसी भी मेथड को यूज़ कर सकते हैं, ठीक है, इट्स ऑन यू, बट इट इज स्पेसिफाई कि आपने एयर स्टैंडर्ड एजम्पशन लेनी है, तो देन यू हैव टू यूज़ these type of formulas, okay, which we already discussed. So either you can use this one or either you can use this one for the air standard one. But for the variable specific heat, then you have to consider for the finding enthalpy values.
ओके सर।
Okay, so now coming towards the second topic, which is the related to Brayton cycle. So we already discussed the ideal case where we are dealing with the isentropic process, because we assume that there are no irreversibilities associated with the compressor and also associated with the turbine. Okay, so now for the actual cases, you already know that it is not possible to develop the isentropic process while dealing with the actual. Okay, so there will be always increase in entropy value. Okay, so for this case, simply the TS diagram is shown over there. So what happened over there? The 2s is the same thing which we already discussed, and 4s point is the same which we already discussed in the previous lecture for the ideal case. Now when we are calling it as an actual cycle, so it means that your entropy for the point 2s will shift it towards the increase in entropy value. Okay, so it will shift it towards the right of your graph, and it becomes the point 2a. Okay, and the similar thing, and it will be only towards the exit of your compressor and the exit of your turbine, because the increase in entropy will be seen at the exit point, okay, not at the inlet point. Then from the point number 3, okay, to 4a, it is the actual process. So 4a also uh, resulted in due to the shift of 4s towards the increase in entropy. So the 4a point will be also shifted towards your increasing point. Okay, so as we already see in the Rankine cycle, whenever there will be isentropic, whenever there will be actual process, we have to deal with the isentropic efficiency of your part. Okay, so in the case of Rankine cycle, we are dealing with the pumps. Okay, so now here there is a compressor and the turbine is the same thing. Okay, so isentropic efficiency of compressor, Ws is the isentropic work and Wa is the actual work, okay, of your compressor. So H2S minus H1 and is the isentropic work, and H2A minus H1 is the actual work. Okay, so you already know that whenever we have to find the efficiency, we have to make um, the minimum term in the numerator and the maximum term in the denominator. So Ws is minimum. Okay, whenever we are dealing with the isentropic process, that's mean that we are supplying minimum amount of work when there will be less irreversibilities. Okay, and we will have to supply more work to the pump when we are dealing with the actual uh, part, or when we are dealing with the irreversibilities. Okay, so this is the meaning of actual and isentropic process. Okay, so similar thing for efficiency of your turbine, isentropic efficiency of turbine, actual over isentropic work. Okay, so in the case of turbine, when there will be irreversibility, so it's mean we are getting less work out of our turbine. So it's mean that the actual term will be less, and your isentropic, so it be there will be no irreversibility. So it's mean that the isentropic process will be more as comparison to the actual work. Okay, so that's why this term will be lower, and now this term will be bigger. Okay, so H3 minus H4A, H3 minus H4A, 4S. The similar thing we already developed in the Rankine cycle also. Okay, so now we will see one question related to the actual cycle, so that you will get some understanding how to deal with the actual Brayton cycle. Okay, so this is a part of example 9-5. Okay, so in the example 9-5, which we already practiced in the previous class, is related to the isentropic process. So the same data we have to use for solving example 9-6. So this is example 9-6 from your book. Okay, so in this case, you have just have to assume a compressor efficiency of 80%. So isentropic efficiency of compressor and isentropic efficiency of turbine 85%. So you have to determine the back work ratio, the fraction of the work that is delivered back towards your compressor, the thermal efficiency, and the turbine exit temperature of the gas turbine cycle. Okay, so this is the problem. So we will see how to find how to solve this type of question. Okay, so you have to note down the data, then we'll move towards the solution. Okay, so again, starting from the TS diagram first. Okay, so I will quickly draw the TS diagram over there. Okay, so this TS diagram I have drawn for the isentropic cycle. Okay, which is the ideal case. Okay, so now we are working on the actual cycle. So definitely the point will be shifted towards the increase in entropy. So this is your point 2A, and here it is your point number 4A. Okay, just to represent the actual cycle now. Okay, so now in the question it is mentioned that okay, so another point which I have left in the previous TS diagram, that your Q in for the actual cycle, you just have to deal with the this area. Okay, so this point between 3 to 2A. Okay, so this is your Q in actual, and whenever you have to find the actual heat rejected, so it is between 4A to 1. Okay, so this is your Q out. Okay, so if it's in the problem, it is mentioned that you have to find the actual Q out, so you have to use 4A enthalpy value. Okay, so now from the part A, we are interested in to find the back work ratio. So back work ratio is the fraction of the work that is delivered back towards the compressor. So compressor in over turbine. Okay, so here we are talking about the actual compressor work and actual turbine work. Okay, so in the previous example 9-5, we already developed the back work ratio, but we have find for the isentropic case. Okay, so now here what we have to do is we have to find the compressor work, that is the actual compressor work, and which is equal to WS. Okay, so this comes from the previous slide. WS is the isentropic work of your compressor and your isentropic efficiency of your compressor. Okay, so WS we have already find in the example 9-5. Okay, so which value is 244.16. Okay, so you just have to go back to 9-5, you will get it. and efficiency of your compressor, isentropic efficiency is mentioned 0.8. Okay, so from here we can easily find the actual compressor work, which is 305.20 kilojoule per kg. Okay, similar thing, we have to find the turbine work also, so which is the actual turbine work. So actual turbine work is equal to efficiency, isentropic efficiency of turbine, and multiply by isentropic work of your turbine. Okay, so this value is 0.85, it is mentioned in your question, isentropic efficiency of turbine, and ws you can go back to 9-5 example and you will get the value 606.6 kilojoule. Okay, so if you can solve it, you will get the value of 515.61 kilojoule per kg. Okay, so now we have the actual compressor and actual turbine work. So simply you have to divide and take the ratio of this. Okay, so you will get the back work ratio, which turns out to be 305.2 divided by 515.61, and it's turned out to be 0.592 of your back work ratio. Okay, so this is that 59.2% of your work that is delivered back towards the compressor. Or if you can compare with the previous example 9-5, the value is 40.3%. Okay, so this means that there is an increase in back work ratio when there are irreversibilities. So this increase is due to the irreversibility that occurs within the compressor and the turbine. Okay, so this is how we have to deal with the back work ratio for the actual cycle. Okay, so you have to note it down, then we move towards the next part. Okay, so here is the part number B. Okay, so in the part number B, we have to find the thermal efficiency. Okay, so thermal efficiency, we already know that thermal efficiency is equal to W net over Q in. Okay, so Q in here we are talking about the actual Q in. Okay, so Q in we can, first we need the value of Q in and then we need the value of W net. Okay, so Q in is equal to H3 minus H2A. Okay, so now we have first we have to find the value of H2A. Okay, so you already know that your compressor actual is equal to H2A minus H1. Okay, so from here we can easily find the value of H2A because compressor actual we already find in the part A. Okay, so we can say that H2A is equal to W compressor plus H1. Okay, so W compressor, the value of WC is 305.20 and plus 300.19, which is the H1 value from the example 9-5. Okay, so simply you can solve it. You will get the value of H2A as 605.39 kilojoule per kg. Okay, so this is the H2A value. So now we have H2A value with us. So simply you have to put the value of H3 from previous example 1395.97 and H2A value is 605.39, or if you can solve it you will get the value of Q1 Q in, sorry. So Q in value is 790.58 kilojoule per kg. Okay, so now the actual Q in is known to you. Okay, so now we need the value of W net. So W net is equal to W turbine, which is the output work, minus input work, which is the compressor work. Okay, so and we are also talking about the actual compressor and turbine work. Okay, so which we already find in the part A. Okay, so turbine actual work is 515.61 and compressor actual is 305.2. Okay, so if you can solve it, you will get the value of W net as 210.41 kilojoule per kg. Okay, so now we have W net with us and Q in, so you can simply divide W net value to the Q in value, so which is 790.58, and it will be equal to 0.266, or you can say 26%. Okay, so if you can compare with the previous example, in the previous example, the efficiency of the cycle is 42.6%. Okay, so it's mean that when we are dealing with the reversibilities, your efficiency will uh, significantly decrease. Okay, so which is now shifted towards just 26%. Okay, so this is part number B, so you have to note it down, then move towards the part C. Okay, so in the part number C, we have to find the turbine exit temperature of the cycle. Okay, so in this case we are interested in to find the T4A. Okay, so for T4A we need the value of H4A. Okay, so H4A we can simply say that W turbine out is equal to H3 minus H4A. Okay, so actual turbine work we have already find. H3 value is known to us from the previous example. Okay, so we can simply use this relation to find the H4A. So H4 becomes H3 minus W turbine. Okay, so H3 value is 1395.97, and W turbine out we have found in the part A, which is 515.61. Okay, so from this we can simply use 880.36 kilojoule per kg is the H4A value. Okay, so now by using this H4A, you have to go to table A-17. Okay, and by using the interpolation against this value of H4A, you can find easily the value of T4A, which is equal to 853 Kelvin. Okay, so this is the come from the interpolation. Okay, so if you have any question, you can ask me, and then we will move towards the next question.
सर
जी
सर हम एफिशिएंसी जो है वो एंथैल्पी यूज़ करके निकाल रहे हैं या टेम्परेचर यूज़ करके निकाल रहे हैं, इससे कोई फ़र्क तो नहीं पड़ता?
जी मैं आपको बताता हूँ. Okay, so here is the question that if we have to find the enthalpy by using the uh, if you have we have to find the efficiency by using the enthalpies or temperature, whether it will be same or different. Okay, definitely it will be different, because one is by using the variable specific heat whenever we have to use enthalpy, and whenever we have to use the temperature, it is from the cold standard assumption, and your actual value is more closer towards the variable specific heat which we have calculated from the enthalpy. Okay, so these two are two different things. Okay, so either it is mentioned in your question, you have to use the variable specific heat, or either it is mentioned in your question, you have to use the cold standard air assumption. Okay, but definitely there will be a difference in your answers for both of the cases. Okay.
मेरी मेरी ओके सर.
Okay, so coming towards the next question, also it is related to the Brayton cycle. Now here we are dealing with the actual Brayton cycle again. Okay, so first you have to read the statement. In a gas turbine power plant working on a Brayton cycle, the air at inlet is 27 degrees Celsius. So your T1 and P1 is known to you in from the question. The pressure ratio is 6.25. The maximum temperature is 800 degrees Celsius. The turbine and the compressor efficiencies are each 80%. Find compressor work, turbine work, heat supplied, cycle efficiency, and turbine exhaust temperature or mass of the air may be considered as 1 kg. Okay, so here is the question. So now we can find how to deal with this type of question. Okay, so now coming towards the solution. Okay, so TS diagram is shown over there. Okay, so for the actual cycle and also for the isentropic cycle. Okay, so from the question it is mentioned that T1 is equal to 300 Kelvin, which is 27 degrees Celsius. Okay, so now our P value is known to you from the question, which is 6.25, and the temperature of your maximum temperature. So maximum temperature is at point number 3. So T3 is equal to 1073 Kelvin. Okay, so an isentropic efficiency of turbine and compressor are equal, which is equal to 0.8. Okay, so now coming towards the solution. So we have to find the turbine work. Okay, so compressor work. Sorry, find compressor work, turbine work, heat supplied, cycle efficiency, and turbine exhaust temperature. Okay, so first we will work on the compressor work. Okay, so compressor work, we can easily say that it will be equal to H2A minus H1. Okay, so compressor work we can say. Okay, so now here we can use the enthalpy value. Okay, but if it is mentioned in your question that you have to use the variable specific heat assumption, okay, so then you have to use the enthalpies values. Okay, and but if it is not mentioned, then you can simply use, because we have the temperature data with us, so we can simply use the code standard area assumption and we can find the value of all the things, which is heat supplied and which is the compressor work, which is the turbine work. Okay, so here in this case I will use the code standard error assumption. Okay, so I already told you that delta H is equal to m Cp delta T. Okay, so this we already know from the previous thermodynamics 1 knowledge also. Okay, so we can simply say that it will be equal to m Cp T2a minus T1. Okay, so here is the compressor work. Okay, so now we have to find the value of 2a, because T2a is not known to us, T1 is known to us from the question. Okay, so we can simply apply one relation for the isentropic process. For T2s, okay, so from here we can find the value of T2s first. Okay, so T2 T1 is equal to P2 by P1 K minus 1 over K. Okay, so now here we can easily find the value of T2s. Okay, and P2 or P1 is known to us from the question, which is the pressure ratio, and K value for air is also known to us. So T2s become T1 is equal to 300, and this is RP value, which is 6.25, and 0.4 divided by 1.4. Okay, so if I can solve it, it turns out to be 506.4 Kelvin. Okay, T2s is known to us, so we already know the isentropic efficiency of your compressor is 0.8. So for isentropic efficiency of compressor, we can write the equation which we already developed in the previous case, H2 minus H1, H2A minus H1. Okay, or we can write also like this, that T2 minus T1 over T2A minus T1. Okay, so now we have all the value with us. T2s is known to us, T1 is known to us, T2A we can easily find, because our main interest is to find T2A, because we have to put in the compressor work equation. Okay, so by using this relation, simply you have to plug all the values in this equation, and you will get the value of T2A, which turns out to be 558 Kelvin. Okay, so this you have to solve it by yourself, because you just have to plug the values in. Okay, so T2A is known to us. Okay, so now simply we have to put the value in this equation, which is WC. Okay, so if I can put the value, the M value is 1, which is given in your question, and the mass of air is 1. CP value is 1.005 for air. T2A value is 558 Kelvin, and T1 value is 300 Kelvin. Okay, so if I can solve it, it turns out to be WC, which is 259.29 kilojoule per kg of your compressor work. Okay, so this is the actual compressor work which we are talking about. Okay, so this is a solution for your first part. Okay, so then we will move towards the next part. Okay, so you have to note it down, then we'll move towards the next question. Okay, so now the second part is to find the turbine work. Okay, so turbine work is similar thing, which we already discussed in the previous, that it is equal to M Cp T3 minus T4A. Okay, so actual temperature. Okay, so now same thing, we have to find the value of T4A in order to find the W turbine, which is the actual turbine work. Okay, so for this we can simply apply another isentropic relation for process 3 to 4s. Okay, and T3 over T4s is equal to P3 over P4 K minus 1 over K. Okay, so we already know that RP value is equal to P2 over P1 or equal to P3 over P4. Okay, because pressure is same. Okay, so from here we can easily find the value of T4s, because we know the value of this one, K is known to us, and T3 value is known to us from the question, which is 1073 Kelvin. Okay, so if we can solve it for T4s, it turns out to be 635.66 Kelvin. Okay, so by using this relation. Okay, so now we have to go towards a T4A. Okay, so T4A, we can simply apply the relation for the isentropic efficiency of turbine, which is equal to T3 minus T4A divided by T3 minus T4S. Okay, so now we have T3 value with us, T4 we have to find, T3 value known to us, T4S we have just find in the previous case, and isentropic efficiency of turbine is 0.8. Okay, so if we can solve this equation for T4A, okay, so we can easily find the value of T4A which is equal to 723.13 Kelvin. Okay, so now T4A is known to us, so simply we can put the value in the equation 1, which is 1.005 CP value, T3 value is 1073, and T4A value is 723.13. And if we can solve it, it turns out to be turbine work, which is 351.6 kilojoule per kg. Okay, so this is the solution for your second desired thing, which is a turbine work. Okay, so now we have to find the heat supplied. Okay, so heat supplied is basically we are interested in point 3 and 2s. Okay, so we can say Q in is equal to mcp T3 minus T2a. So m value is 1, cp value is 1.005, T3 1073, T2a value is 558, which we already find in the previous part. Okay, so simply we can solve it, and we will get the qm value, which is 517.57 kilojoule per kg. Okay, so now cycle efficiency is left. Okay, so for cycle efficiency we can say that w net over q supplied. Okay, so q supplied is basically q in. Okay, so this is known to us, so w net is equal to w turbine minus w compressor over q supplied. So WT is known to us from the previous part, which is 351.6. W compressor is equal to 259.29 and divided by QS, which is 517.57. And it turns out to be equal to the efficiency, which is equal to 0.1783, or we can say it will be equal to 17.83%. Okay, so this is the isentropic efficiency of your the efficiency of your cycle or Brayton cycle. Okay, so now another thing which is desired from your problem statement is to find the turbine exhaust temperature. Okay, so this is the same temperature which we are talking about is 4A. Okay, and T4A we already find in the previous step, which is equal to 723.13 Kelvin. Okay, so this is also known to us from the previous part. Okay, so now this is the solution of the question while dealing with the actual Brayton cycle. If you have any question, you can ask me, or you have to note it down the solution, then we will move towards the next slide. Okay, so here is the question which you have to solve. Okay, so by yourself. Okay, so this is the same question which we already solved in the start of this lecture. Okay, so only some data is different over there. Okay, so you will get 0.2 absolute marks for all the students who will send it to me in the clear way. Okay, so you have to note it down, then just stop at this point.